My name's Lucas, and this is my MediumISP, the split flap display. You might have seen displays like this before. They're quite popular in like old airports and train stations, with displays like airplane, like where they're going to and the departure times. Saw one in a Krispy Kreme that I went to recently, and also the Eden Center. So I thought it was really cool, so I decided to make my own. In this video, I'll be explaining how my project works, why I made some of the design choices that I did, and yeah. So in basic terms, how split flap display works is by cycling this spool of flaps you can see right here, and they have characters printed onto them. Inside the display here is actually the spool with all the different flaps and pinned in between. In my design, I decided to have 40 flaps to include every single letter, number, and hashtag, exclamation mark, and the @ symbol, and just a blank space to fill in the remaining spaces. From this side view, you can see two of the other major parts of this normal capsule here, the normal module, the stepper motor, and the actual PCB. The stepper motor is what actually turns the spool of flaps. In this picture, you can see 4 wires, red, black, green, and yellow too. These 4 wires are the only thing that connect each module to each other, and they carry power in red, ground in black, and SCL in green, SDA in yellow. I'll get into those other two, SCL and SDA, in a little bit. Basically, the PCB that you can see here is what takes the information from those 4 lines, and it decides how much to rotate the stepper motor to get to its final goal of whatever character is trying to go to. These 4 lines also go through the ceiling that you can see here, and you can also see them going along the top of every single module. This is just to carry them from one module to another, and I really couldn't find any other place to put them. The flaps kind of take up the whole box. Which is a bit hard to see is this magnet sensor, and because it's partially going through the casing, and it's soldered to the back side of the PCB. This magnet is how the PCB, which is controlled by the ATtiny84, actually knows how far to rotate the spool of flaps. Basically, rotates the spool blindly until a magnet is detected. And at this point, I've arranged it so that when it detects a magnet, the spool's at the letter A. And then, depending on which character it wants to go to, rotates this many steps. You can see on the screen the actual code of how many steps it goes, depending on which letter it receives. So I had to manually test to find out these numbers, because all of them are not perfect. There's different amounts of friction for each part, so that's why they're not linear. Back to the PCB, it's controlled by the ATtiny84, which is an Atmel microcontroller, and it's kind of the brains of this PCB. It takes the input for the 2 SDA and SCL wires and the magnetic sensor, and tells the ULN 2003 what to do with the stepper. ULN 2003 is a Darlington transistor array. The way it works is almost by acting like an old-fashioned switchboard. It takes weak signals from the ATtiny84 and it kind of tunes them up to safely control the relatively high power demands of the stepper motor. It also has flyback diodes to protect the ATtiny84 from any current going backwards. So this is the same setup for all 4 of these modules, which makes my project super modular because it's really easy to add another module or to get rid of one. And the assembly for another module is the exact same, with only 4 wires connecting each one. The one module that is different is this very first one. As well as basically the same as everything a normal module has, it also has this little section that sticks out the back. On it, there's a second PCB, and below it is space for a battery. The actual battery is a 7.4 volt, 2000 milliamp LiPo battery. I took this from an RC car, and I decided to use this instead of the standard 9 volt battery because this project has a lot of motors included. It requires a lot more current than a 9 volt battery has, hence the 2000 milliamp hour current rating. However, this introduces the problem of the 7.4 volts. So I simply stepped it down by soldering a 5-volt voltage limiter directly onto the power lines. On the second master PCB, that's the name of this PCB, it is controlled by a more powerful ATmega 328P, which is just another Atmel microcontroller. It also has the main on and off switch, which can turn on and off the entire project, and a reset button. And finally, this is also where those 4 wires originate from. The green and yellow wires are for I2C. This is a form of communication to control systems with just 2 wires. I2C stands for Inter-Integrated Circuits, which is kind of a weird name. I don't know why it has inter twice. And the SDA, or the green line, carries the data, and the yellow line, the SCL, carries a clock signal, basically keeping everything in sync. In I2C, there is the master device, which is the ATmega in this case, and multiple slave devices, which are the ATtiny84s. The master can determine which ATtiny84 is which because of their identifier tag. Because the slave devices are microcontrollers, I can manually set their tag. So, for example, I've set the first module identifier tag to be OX01 and the second to be OX02, and so on. For simpler devices like a temperature sensor or a light sensor, they have their identifier tag built into them. So if you're using those in I2C, you have to look them up. But here I can make my own. Finally, onto the actual case. There are 2 neat kind of weird things. First at the top and then at the bottom. On the top, there's quite a large lip. This one partially touches the flaps and holds them back a tiny bit. This is actually because when the spool, if it were to rotate normally, the flaps would actually stick together. So 3 or 4 flaps would fall at once. The lip removes this problem by kind of adding some tension into the system, so only one flap rotates at a time. The next weird thing is the lip at the bottom. First of all, this one's just for show and really serves no purpose, but the wedge right behind it does. It holds back a select number of flaps, creating a solid barrier. Without it, the flaps just kind of hang there, but with them stacked together, it provides a kind of solid barrier for the falling flap to land against, stopping it from swinging around and making it easier to see. Falling on this stack of flaps is also what makes the split flap's iconic flapping sound that you can hear when it's rotating. Well, that was it for me. This project's super cool. I really like how versatile it is, and I can really display anything I want. This was my MediumISP, the split flap display. Thanks for watching.